Okay. Chapter 16 is about predicting populations. Of everything we've covered covered this year so far in statistics, this is probably the most heavily covered topic. If you want to know something about a given group of people or a given object, rather than going out and asking every single person or researching every single object in that population, you collect a sample. So ask maybe 50 to 100 people. And then from that sample of 50 to 100 people or whatever you may choose, make a prediction about the entire population. So if you want to know how many people in Adams County are Democrat, you might just go to the Adams County phone book. You ask the first person on every page of the phone book. So you might ask 200 people, are you a Democrat or are you a Republican? And then based on what you get there, you can make a prediction about the entire population. Does that make sense to everybody? Okay. So this is probably the most widely used concept in statistics because it cuts down on the cost of research. So here's an example. In 2010, Pew Research, which is just a company that does surveys, Pew Research asked 156 random Facebook users if they updated their account daily.
156?
156 random Facebook users if they updated their account daily.
Listen again.
1 second, sir.
Well, we need the Chromebooks.
In 2010, Pew Research asked 156 random Facebook users if they updated their account daily. 48 did.
Well, it meets the rules.
48 did. So the question, can we use this as a predictor for all Facebook users? Can we use this as a predictor for all Facebook users? 48 out of 156 update their account daily. Is that an accurate representation? Is that something we could use to represent the entire population? The same 4 concepts apply. There's 4 assumptions that have to be met. The first 2 is independence and random. In 2010, Pew Research asked 156 random Facebook users. That word random tells us that the independence and the random assumptions have been met. If you're random, then that means it's not dependent also. So if it states that it's random, it meets the random independence assumptions. There was also the 10% condition. Did it say you had to ask more than 10% of the population or less than 10%?
Less than.
You had to ask less than 10%. Because if you do ask more than 10% of the entire population, you run into issues with independence. Okay? So it has to be less than 10% of the population. If you ask 156 Facebook users, well, that would mean if that was more than 10%, then that would mean that there's only like 1,560 people in the whole world that use Facebook. Okay, so is 156 definitely less than 10%? Yes. Okay, there is a lot more than just 1,560 people that use Facebook. So therefore, we're definitely less than 10%. So we've met that assumption. And then the 4th assumption is the success-failure assumption. That says we need how many of each?
10.
At least 10 of each. Okay? We've got 48 people who have technically committed a success. Since it's a study about Facebook users that update their account daily, a success would be a person that did do that. So we have 48 successes. Okay, so 48 successes. And if there's 156 total, that means we have 108 failures. Do we have at least 10 of each?
Yeah.
Yes. So we've met all 4 assumptions. So the question, can we use this as a predictor for all Facebook users? The answer is yes. So yes. We can make a prediction about all Facebook users. And if it's all Facebook users, is that a sample or is that the population? Okay, so all Facebook, so that's the population. Okay, so yes, we can make a prediction about all Facebook users, which is the population. Using this sample of 156. The sample is the 156 people we asked. We're interested in learning about the entire population of Facebook users, all users of Facebook. We met the 4 assumptions, so therefore, yes, we can use this sample of people, this group of people, to make a prediction about the entire population. Okay, but then there's this but. And with anything you do in statistics, there may be error. And what this is going to be called in this section is it's going to be called the margin of error. We have a specific margin of error. And if we want to control for error, we don't say, hey, 35% of Facebook users update their account daily. If we want to control for error, we have to create a what?
Standard deviation.
Well, standard deviation helps us create it.
95% confidence.
A 95% confidence interval. Okay? So if we want to account for the error, we create a 95% confidence interval. So we can't say, hey, we know this is how many Facebook users update daily, but we can say, based on our sample of 156 people, we are 95% confident that the number of people who do update is between this value and that value. Okay? So we can use a confidence interval to come up with that. So,
Do you want us to write that down?
you wouldn't need to. We're getting ready to, if you want to.
So pretty much whenever we're looking for error, we're going to be using the 95% confidence.
Because that gives you how much above and how much below your prediction is still considered an okay amount. Yep. So, let's think. Let's think. If our survey is conducted appropriately, which is this survey being conducted appropriately?
Yeah.
Yes, we've met the 4 assumptions. If our survey is conducted appropriately, %95 of the time, the sample mean or proportion. Remember, the mean is when you're talking about quantitative, the proportion is when you're talking about categorical. It's the same concepts though. 95% of the time, the sample mean or the sample proportion, just depending on what categorical or quantitative data that you're dealing with, 95% of the time, that answer will be within how many standard deviations? Will be within standard deviations of what?
The population.
The population mean or proportion. Okay, the concept applies whether you're dealing with quantitative or categorical, population mean or population proportion. Remember, mean is quantitative, proportions is categorical. In this problem, what are we dealing with? Quantitative or categorical?
Categorical.
We're dealing with categorical. Either they did update daily or they did not update daily. There's either a success or there's a failure. It's a failure. It's a group ownership. So this example is categorical. Okay, so 95% of the time, okay, theoretically, if we go ask a random sample, we should get P. We should get the population proportion. We should get P or we should get mu, right? Remember, P is proportion, mu is mean. But they both represent population. 95% of the time, our samples data of the time, our sample data should fall somewhere in this region.
Or what should fall?
Do what?
Or what should fall?
Our sample should fall in that region. Our sample 95% of the time should fall in that region. So if we were to look at just the very extreme, just the absolute extreme, the worst case scenario, 95% of the time,
Not report to the office, please.
the worst case, the absolute 95% of the time, the worst thing that could happen is our sample mean or our sample proportion should be 2 standard deviations below, right? This is the absolute worst case scenario, being 2 below, 95% of the time. Or 95% of the time, the worst thing that could happen is that our sample could be at the very extreme, which is also 2 above. Okay, so the orange curve in the middle is our population, the curve based on our population. The empirical rule says 95% of the time, the worst thing that could happen is our samples curve is either over here at negative 2 standard deviations below the population, or positive 2 standard deviations, 2 standard deviations below, or anywhere in between, right? This purple curve could be anywhere in between these two curves. Yes, sir.
Is there a reason for the going to the right, but P hat over X or P hat?
Or X, it's just be or X bar. Yeah, my bar is.
Does one of them have to be negative because it's negative?
Well, and the 95% confidence interval covers the negative and the positive.
Okay.
So worst case, so these two are the same data set. This is the worst negative that could happen. This is the worst positive that could happen 95% of the time. Now, with that said, if we are at the most extreme sample on the bottom end of things, how far is the population away from it?
1 standard deviation.
Two, what, above or below the sample? Oh, listen to what I'm saying. We're talking about looking at the sample. If our sample is the most extreme sample is 2 below, how does the population compare to it? It is 2 above. Okay? And if our sample is at the most extreme as being almost the highest possible outcome, the worst case scenario is if that happens, the population is still just how much below? 2 below. So that means that the concept of that 95% confidence interval still holds true. If 95% of the time, our sample is going to be either 2 standard deviations below or above the population, then that means if you're to collect a sample appropriately, 95% of the time, the population should be also within 2 standard deviations of the sample. Does that make sense to everybody? If not, now it's time to speak up. This is a big concept.
I don't.
I can repeat it again if you want me to.
Yes, please.
Okay. Confidence interval, Anna, says 95% of the time, our sample, which are these purple graphs, will either be 2 below or 2 above or anywhere in between. At the most extreme, in comparison to the sample, the population is either 2 above or 2 below. So that means also 95% of the time, the population is always going to be within 2 standard deviations of whatever sample you collect.
Okay.
So why is the samples at 2 and -2 again? Is that
Because the 95% confidence interval says that's the most extreme thing that should happen 95% of the time. 2 above and 2 below.
why is the confusion I guess there?
Why is this X bar here?
Yeah.
Because this concept applies for sample proportions and sample means. Just like P is the population proportion, U is the population mean. JJ, is that okay?
So we do the first graph. That's what we got. That's between the things.
This
And
is
then
the
the other-
population.
And the next two for those only stand for the extremes.
This is the population. Yeah, what should happen.
All right. The
The
original
two
is population.
purple, the two purple are the most extreme that could happen 95% of the time when you conduct a sample.
Okay, that makes sense.
So if you conduct a sample 95% of the time, this population will always be within 2 standard deviations of whatever sample you collect also.
So if it was to be outside of it, then it still would be too low because then your and you would move, right?
Yeah, well, if you had a sample that was outside the 2, then that means our sample was abnormal. So if our sample is abnormal, then that means the population is more than 2 standard deviations away from it.
So what's the too low bottom?
Well, if you conduct an appropriate sample, it will always be 2 above or 2 below. Okay? This only applies if the sample is conducted appropriately. And that's like those questions that we said, does this seem to be an abnormal sample? Sometimes they will be abnormal. They're not conducted appropriately. But if they're conducted appropriately, it will always be 2 above. The population will always be 2 more or 2 less at the most of whatever we collected. Okay? So this 2 above and 2 below is what tells us our margin of error. Okay? So what we can say is, so we can say also 95% of the time the population of the time the population is within 2, and guys, there's a little change in wording right now. 2 standard errors of the sample.
Is there any particular reason why you skip line?
No. No particular reason. So we can say, go ahead. So we can say also 95% of the time the population is within 2 standard errors of the sample. Standard error is just, in all the problems that we've done so far, you've known the population standard deviation. Okay? If you collect a sample and you know nothing about the population, if you collect a sample and you know nothing about the population, do you know the population standard deviation? No. So not only are you predicting what the population's mean should be, but you're also trying to predict what the population standard deviation would be. And the only way you can do that is to use your data to make a prediction about the standard deviation of the population also. So a standard error is just when you're using your data to calculate what would be considered the standard deviation of the population. It's a prediction. There's 3 ways to do this. 3 ways that we can conduct this kind of concept. Yes,
I have a question about the graph.
yes, sir.
So whenever we get, if it's not abnormal, it'll always fall in either between 2 above what we get or 2 below what we get, right?
Correct. So we're going to create a 95% confidence interval, not about the population, but about our individual sample. And then the 95% confidence interval of our sample will allow us to say 95% of the time the population should be somewhere in between here and here.
So if we did of our population and it was to fall on the outside, then we could count it as abnormal.
Well, no, we're making a prediction about the population, so we don't have anything to compare to. in order to know that it falls outside of the 95% confidence interval, you have to have you have to know the population compared to it. So how does the population compare to the sample? We're talking about making a prediction about the population without knowing it.
So what if it is outside of
Courtney's
Well,
done supposed to be off.
We won't know. So we'll just say we're 95% confident that it's in here. But it's just you're just predicting here's what the population may be.
Oh, yes.
See, in the past we've always known the population. That's been told to us. The number of people in the United States who are Democrat are 48%. How does your sample compare? Now we're saying let's go out and collect 200 people and use that to make a prediction about how many Democrats are in the United States.
So we're technically taking our size and comparing it to the if we didn't
No comparison. Just making it using it as a predictor for.
no, that's what I mean. Like if we had like the population of Ohio and it was like 12,000 people,
Yes.
but we didn't know if any of them were Democrat or not, and we found out our little town.
Correct. We
and
can
we found
use.
this, we could use that for the whole.
Correct.
Okay. Oh, okay. Nice.
We're using our what's reasonable sample to collect as a predictor for whatever the population we're interested in.
So now we're starting to get into like covering all of the possibilities, right?
Yeah,
Instead of
so-
just, like, the stuff between there.
Yeah, so basically what it would be like, okay, I mean, I haven't decided how you guys do a project on this, but an easy project would be to come up with a survey question, something you're interested in knowing about. Pick a population that you're interested in knowing about. So for me, an easy example would be, do you like school food? Yes or no? It's either yes you do, no it's not. So it's categorical data, right? And you say, okay, I want to know about all the students at West Union High School. So there's 600 and some students. Well, rather than going and asking all 600 students, you go and ask 60 students. You get their answers. And then you say, okay, I got that 38% of school or students at West Union High School do not like, I got 38% of my sample do not like the school food.
Mr. McCann,
Yes,
is Kristen Unger in there?
yes,
Could I have her to the office? She's supposed to be giving some blood.
sure.
Thank you.
So if we say we collect a sample of say 60 students, we get 38% of them. We can't say, well, 38% of the entire school doesn't like the school food. It's just 38% of our sample. But we can create a confidence interval based on sample. We can say we're 95% confident that between 31% and 45% of the school do not like the school food. So we can give a range of possibilities.
So we can do the 10%, we just can't do more than 10%.
Correct. Good. All right. So there's 3 ways to do this. Okay? It's the same 3 methods that we've been doing all year. Well, same 2 methods. One way to do this is give categorical data. Categorical data means we're going to use what? Means or proportions? Proportions. So we're going to be using percents, decimal. Okay? So in terms of categorical data, we're going to use p hat, which is our sample, to predict p.
Are we doing all of this with or without the knowledge of half of the population?
You don't have to decide the population.
That all to be able to.
Proportions is. Categorical data deals with proportions, and we're going to use the proportion of our sample to make a prediction about the proportion of the entire population. The second method would be quantitative data, which means we're talking about means, right? The average. It works for modes, any kind of quantitative data, but typically means. And then this is where we use X bar to predict mu. Now, I said there's 3 ways to do this, and we've always just done categorical data and quantitative data. There's 2 subcases for quantitative data. Subcase 1. Subcase 1 with quantitative data. Population standard deviation. That's that sigma, right? This does not happen very often. But if you know the standard deviation of your population, then there's one way of doing this. Population standard deviation, sigma, is known. If you know that, there's one way of doing this. Okay? This typically does not happen in a real-world study. Typically does not happen in a real-world study. Because if you know the population standard deviation, well, in order to know the population standard deviation, you have to know the population's data, right?
Yeah.
And if you know the population's data, why wouldn't you just know? If you know the population's data, you can just find mu. Okay, so that typically doesn't happen. But there are certain cases where if you want to make a prediction about, the student's average ACT score at West Union High School, you could collect 30 students' ACT scores, and you could use that sample as standard deviation, right? We could also go on ACT's website and use the population standard deviation because the ACT company says here's the standard deviation of the entire state. Does that make sense? So there is some special cases where you will know the population and you won't have to depend on just your sample as standard deviation to do the calculation. But subcase 2 is when the population is not known. This is more common. If you want to know how many people in the school like your lunch, like the school lunch, you're not going to know the standard deviation of the entire population unless you go ask every single student. So typically we don't know the population standard deviation. That's more of a more common study when you're conducting your own study. When you're doing something comparative, you run into subcase 1. When you're just trying to do a brand new study, you typically do subcase 2. You don't know the population. That's the whole point. Okay, so if you look here, guys, 3 ways to do this. Categorical data, that's one way. You have quantitative data, where sigma is known. That's the second way. Or you have quantitative data where sigma is not known. That's the third way. Does that make sense to everybody? There's our 3 different ways that this could happen. Okay? The first one we're going to go over is categorical data. It's the same overarching concept. It's the same overarching concept, but now we're going to talk about it with categorical data. If we're dealing with categories, if we're dealing with categorical data, we don't use what's our measurement? It's a what?
It's a
percentage or a proportion. And if you're trying to use your sample to make a prediction about the entire population, how many samples are you looking at? How many samples? Not the sample size. How many samples?
30.
No, sample, not sample size. How many? You're looking at 1.
2.
You're taking your 1 sample and using it to make a prediction about the entire population. When you do categorical data, it's called a 1 proportion Z interval. You're going to create a 95% confidence interval. You are going to create a 95% confidence interval. So it's an interval. It's a 95% confidence interval that is based on a Z-score. Because we're going to introduce something other than Z-score in this chapter. It'll be also we'll have T-scores. It's the same concept. It's just another chart. So instead of reading the Z chart, you just go to the T chart. It's the same concept. Okay.
Is that what you're talking about with the W too?
Yeah, it's just a different score. It's a different way of measuring it based on the data you're dealing with. And we're doing it with 1 proportion. So it's a 1 proportion Z interval.
How do you know which one to use?
If it's categorical data, you'll do a 1 proportion Z interval. If it's quantitative data, then there'll be a couple other titles I'll give you later on.
Why didn't we use T-scores when we were doing what we just did?
Because the T-score is used when we'll get to when we use T-scores. We always knew enough information to use Z-scores.
Oh, okay.
We always had enough information to use Z-scores in the past. But if you don't know the population standard deviation, Z-scores aren't good enough, so we got to use T-scores.
Why would you use both of them? Both of them.
All right. So categorical data, 1 proportion Z interval. We have a formula for a 95% confidence interval. What was our 95% confidence interval in the past? It was P.
I know this one now.
It was P minus 2 standard deviations of P hat and P plus 2 standard deviations of P hat, right?
Oh, that's clear.
And when we're talking about categorical data, this is our 95% confidence interval. But that's when you're making a confidence interval around P, and P is the what?
P is the population.
Population proportion. We don't know that. So our center of our curve is not going to be the population, it's going to be our sample. So instead of P, it's going to be P hat. Instead of P, it's going to be P hat. And now we've got to take away 2 standard deviations of P hat. But let's remember something. In order to calculate the standard deviation of P hat, it was the square root of PQ over N. So in order to find the standard deviation of your sample, you had to know the population proportion. Do we know that?
Yeah.
No, that's what we're trying to predict. Okay? So we don't have a standard deviation of P hat now. We have what's called a standard error. Okay, these are called standard errors.
If you mix these up on the test,
And then it's wait, I made a mistake. It's not P hat minus standard error, it's P hat minus how many?
2 standard errors.
2 standard errors. And then it's P hat plus 2 standard errors. Now, the formula for standard error pretty well makes sense. To find the standard deviation of P hat, it's the square root of PQ over N. Do we know P?
No.
No, we collect our sample. What's the only thing we know?
sample.
We know
The sample size.
we know P hat and we know N, right?
Yeah.
So our formula for standard error is going to be the square root of P hat Q hat over N. Yeah, I'm gonna put that on there also. I wish you just used the all call. Yes. I'll be down when the class is done. Thanks.
Are you doing blood too?
I am.
Cool.
I tried.
We got
Hey,
V8s.
were
Don't
you there
get
last
the
week when I
V8s.
vomited everywhere?
They have some
Mr. McCann?
It's tomato juice.
Do what?
Were you there whenever I vomited everywhere?
I was there right before.
Oh,
Yeah, 'cause
okay.
I
I
saw
left and then it happened like
Oh,
the
no,
next day.
Mr. King was there whenever I vomited everywhere.
They were talking
So-
about you vomiting everywhere.
Okay.
I know.
Standard deviation of P hat is dependent upon knowing the population proportion P. We don't know that, so what we do is we come up with what's called the standard error. And that's where we use P hat and Q hat. And guys, Q hat, that's easy. It's just 1 minus P hat. If you have 60% success in your sample, the probability of failure in your sample would be 40%, 1 minus 0.6. Okay? Now, the reason we have to have this new formula is because we don't know P. And if you don't know the population, we can't use it to calculate standard deviation. So, does everyone have this written down?
Yes.
Okay. Let's go to the next page. Going back. Pew Research. Okay? Pew Research collected data on how many Facebook users update their account daily. They either update their account or they don't update their account. That's what kind of data? Categorical. So our sample size was what?
N equals 156.
156. They asked 156 people. And P hat. It was 48 over 156. That was a big issue on the last test. Was people were wanting to put P hat was 48. P hat is a proportion. Proportion is success over total. 48 out of 156. Okay? We can type it in the calculator. It's 0.3077. Okay? For the sake of notes, I'm going to just make that 0.31. 31%. So in this sample of 156 people, 31% of them updated their account daily. That does not mean 31% of the entire population updates their account daily, but it gives us a way to make a prediction about the entire population. So what we can do now is we can create a 95% confidence interval to predict P. And remember, P is the proportion, is it the proportion of our 156 or the proportion of all? It's the proportion of all Facebook users. To update daily. Because if 95% of the time, an accurate survey will be within 2 standard deviations of what really happened, and that means the entire population should always be within 2 standard deviations of our accurate sample. So we're going to create a 95% confidence interval, and that's p hat minus 2 standard errors of p hat, and p hat plus 2 standard errors of p hat. That's what we're going to create. In order to create this, we need to know what p hat is, which we do. We've already figured out p hat. P hat is 0.31, right?
Yeah.
And we also need to know standard error of p hat, which we have a formula for that. P hat q hat over n. 0.31. Q is 1 minus 0.31, which would be point what? 0.69. That should make sense because if 31% of your sample updated their Facebook daily, then that means 69% did not. Over n, our sample size. 156. 0.31, that's not point, that's a negative. 0.31 times 0.69 divided by 156, square rooted, gives us 0.037. 0.037. So our confidence interval is going to be p hat 0.31, take away 2.037, and p hat, which is 0.31, plus 2.037. Typing this in the calculator, you get 0.236, comma 0.384. If we want to convert this to a percent, it would be 23.6% to 38.4%. How you report this is very crucial. Okay? Reporting the results. Reporting the results. We will work on reporting the results on Monday. Okay? There's several ways.